Alrighty, folks. So today we're talking about section 3.7, which is adding another rule to our arsenal. So far we've had the sum and difference rule, we've had the constant multiple rule, we've had the product rule and the quotient rule, and today we're going to have the chain rule. Right, so all of the others sort of tell you what kind of thing you're dealing with in their name. Use the product rule when you have a product of functions. Use the quotient rule when you have a quotient of functions, so on and so forth. Chain rule doesn't, but the chain rule, I guess, could, by that nomenclature, be called the composition rule, because it's how you take the derivative of two functions that are compositions, or the composition of one function with another. And that rule is that you take the derivative of the one on the outside and you plug the inside in without taking the derivative, and then you multiply it by the derivative of the inside. So all these problems are going to boil down to figuring out the outside function and the inside function. So what's being plugged into what, and then putting those to these pieces. All right, so we'll need the outside function and the inside function. We'll need to be able to find the derivative of both of them, and then we'll need to put these three pieces together. A couple of other rules that this section has that are really just byproducts of this rule, but they're ones that show up often enough that it's handy to be able to just use them without redoing the chain rule every time in your head. And that is the generalized product rule that says if you're taking the derivative of some function that's been raised to a power, well, that's going to work a lot like the power rule, except this g here is that inside function, so we need to multiply by the derivative of that g. And then we also have d dx of e to a function of x. It's going to be equal to e to that function of x, just like you'd expect from your standard exponential derivative. But here, this g of x is the inside function, so we need to multiply by the derivative of it. Right, so that's really just two specific instances of the chain rule, but they're two that show up often enough that it's not a bad idea to have it in your mind as its own rules, as their own rules, so you don't have to worry about rethinking about the chain rule over again. So some problems. And we're always going to find the derivative of the function given. So 1 . And one thing to be careful of when you use any formulas like these is that this f in the formula and this f in our problem are not the same one, right? The f in the problem is the entire function altogether. The f in the formula is the outside function, right? That's why when I was listing that off, when I was saying in words this formula, I tried not to do too much f and g, but just tried instead to focus on the idea of outside function and inside function, right? In this case, we don't have to worry quite so much about outside versus inside because it actually matches up with one of our byproduct rules, right? So we know that f prime of x, right, this is e to the g of x, right? So our rule says we need to just repeat it again, but then multiply by the derivative of the exponent, and we have that from last class, if we don't remember off the top of our head. I certainly don't. I like having a reference sheet. Right, we might want to simplify that up a little bit just so it doesn't, so no one can get confused as to whether that should be subtraction or product by a negative. And there we go. Let's see. Let's have f of x equals sine of 3x squared plus 2x minus 1. Right. So here I said sine of, right? Anytime you say of in the middle there, it's kind of an indication that there's some composition going on. At the very least, of is a word that we use for composition. So I need to think about my outside function and my inside function. Right, and in this case, sine is definitely the thing that's outside everything, right? It's on the edges of our function. So sine of x is the outside, and the inside is that polynomial. Then we want to find the derivative of the outside, right? And again, according to what we had last time, that's cosine of x. And the derivative of the inside, that's just a lot of power rules, right? So we bring that 2 out front, and we get 6 to the x. The next term's just linear, so we take the coefficient. And the next term is constant, so it goes away. So now we need to take these pieces and put them together, right? So the chain rule says, first take the derivative of the outside and plug the inside in. So the derivative of the outside is cosine, and we want to plug the inside into it. Right, and then we want to multiply by the derivative of the inside, which we figured out was 6x minus 2. Right. Let's see. So this is a function that we actually could have done before this section. It just would have taken us a lot of time and a lot of patience and a lot of paper, right? Because we could multiply all this out, right? We could multiply 3x plus 7 times 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 3x plus 7. And we would have gotten a 6-degree polynomial, and it would have taken us forever. But then we could take the derivative using using the power rules. But now, I never made us do one of those because, frankly, that sounds wretched. But now we can do it much easier by using the generalized power rule, or this byproduct of the chain rule involving powers, right? So here, 3x plus 7 is the g of x that's being raised to a power. So our rule says that when we want to take the derivative, we're going to, just like before, bring that power out front and have the rest of it change by just bringing that power down by 1. Right? And then the chain rule part of it says then we got to multiply by the derivative of the inside. Right? Now that's just a linear polynomial, and so we know its derivative is 3. Right? So let me just write that over here. Right? So 3 gets put in there, so we get 18 3x plus 7 to the 5. So it works the same sort of way as we would use the power rule for something else. It's just if the thing we're taking the power of is more complicated than just x, we also have to multiply by the derivative. What number was that? That was 3. So sometimes we can even have to do it a couple times in a row, but we can combine some stuff. Right, so... Right, and we know that for taking derivatives, it's often nicer to think of these roots as powers. Right, so maybe we rewrite this as 1/2 and 1/3 powers. And similar to the way this is before, this looks a lot like a power function, except the inside is more complicated. Right, this is our g of x instead here. So we know that f prime of x is going to look like 1/3 times all that stuff negative 2/3. But then we know that we're going to need to multiply that by the derivative of this, right? Because that's way more complicated than just x by itself. So when I do that, that's not going to be too bad. So 3x plus 1/2 to the 1/2 to the negative 2/3. Right, I can use the sum rule. 1 turns into a 0. And this looks like it's going to be another application of the chain rule, right? Because it's another power function, or it's kind of like a power function, but what's underneath the power is more complicated than x. So I know that's going to be 1/2, then all that stuff to the power minus 1. And then I need to multiply it by the derivative of the inside. All right, so we get 1/3 times 1 minus 3x plus 1 to the 1/2. All of that to the negative 2/3. That 0 can go away. So we just have negative 1/2 3x plus 1 to the 1/2 times 3, because that's what the derivative of this is. Right? And we could simplify a little bit, right? Multiplication doesn't matter the order, so those guys can cancel. And I can pull the negative 1 out front. So, in fact, I can pull the negative 1/2 out in front. And I can move this piece to the denominator so that its power gets positive. Right, so that would probably be a nice way to simplify this. I can't, these two guys can't cancel each other out in any way. For one, because up top it's not a factor, and you can only cancel out factors on fractions. Right? And for another, it's specifically underneath some other root. Right? So you can only cancel factors, and you can't just pull things out of roots in order to cancel them. So that's probably about as simple as we can make it. Right. So let's do one more. Get some more practice on this stuff. Let's say f of x equals tangent of 1 over x squared plus 1. Right? So here it's not one of our sort of byproduct special case rules, so we just need to find the outside and the inside. Right? The outside's definitely tangent of x here, and then we're plugging in 1 over x squared plus 1. So the derivative of the outside is secant squared x. It's one of the things we got from last section. And now here's where something that I mentioned when we first learned the quotient rule can come up. Right? I can write this slightly differently. And writing it like that gives me two options. Right? Or having both of these forms gives me two options. This one I have to use the quotient rule for. Right? It's a fraction. There's an x on the denominator. I have to use the quotient rule if I write it like this. This one, I can use the chain rule. Specifically, I can use that generalized power rule that we learned right here, right? And say that we bring that -1 down front, and we lower the power here by 1 for a -2. And then we take the derivative of what's inside the parentheses, right? And so we could rewrite this if we wanted. This is -2x over x squared plus 1 squared. And either one of these is fine, right? If we did the quotient rule, and high, d high, so we'd get low, d high, minus high, d low, over the square of low we go. Hey, turns out to be exactly what we found before, right? So those are both perfectly legitimate ways to work it out, and that's true of every problem that involves a quotient rule, right? You can use the quotient rule, and that's fine, or you can rewrite it so that the denominator is now a factor, and it's being raised to the -1 power, and use the chain rule instead, right? So both of those are perfectly legitimate ways to take the derivative of something like that now that we have the chain rule. So, that all being said, this is what we were really working for. So, the derivative of the full function is going to be the derivative of the outside, whoops, with the inside plugged in, times the derivative of the inside. So derivative of the outside with the inside plugged in times the derivative of the inside. So this is the derivative of outside, inside plugged in, and then derivative of the inside, right? And that's all there is to the chain rule. The biggest part of this tends to come down to recognizing what the outside and the inside are, right? So that's a problem, that's a type of problem that you most likely saw in your pre-calculus class as soon as you learned what a composition was how to decompose a function. And that is because of problems like this, right? Primarily, the reason why you want to decompose a function is to do the chain rule on it. That's sort of the biggest application of it that I'm aware of. And it mostly comes with practice, right? So this is a place where just going through and making sure you can figure out how to decompose it, why I decomposed it this way, and what the pieces are, is one of the more important things for the chain rule. So next time we'll be skipping over to 3.9, where we learned both some new specific formulas for taking the derivative of specific functions, and a couple of nice tools for taking derivatives in general. So I'll see y'all next time.